You know what a vector is, hopefully. Uh, Definition of vector space: a real vector space V is a set of elements together with two operations, addition and scalar multiplication, satisfying the following properties. All right, should all look very familiar. If it's together with these two particular operations, addition and scalar multiplication, you're talking about a linear combination. All right, because if you can put your columns, which are your typically that's how we're referencing the vectors, if you put them together using those two operations, 64 for those of you still looking. If you put them together using only those two operations, then you're looking at the linear combination of the columns of the matrix. So that would be in theory, the span of whatever the vectors are that make up the matrix. All right, so that's why we're basically looking at a copy-paste of the properties from 2 units ago. So, yeah, this is all old news. And also pretty commonplace stuff. But it's the subspace stuff that's new. So the properties that you see before are just kind of a little bit of a refresher, but this is where we get into the new stuff. All right, definition of subspace: W is called the subspace of real vector space V. All right, so again, the linear combination of the columns of the matrix. If W is a subset, subspace subset, that makes sense, of the vector space V, W is a vector space with respect to the operations in V. All right, so it itself has to be a vector space, but in addition to that, it then has to also be a subspace, a subset, sorry, bless you, of another vector space. Right, that would make it a subspace. Right, so you think about in regular algebra, you have sets and subsets. Right, you can think about that in probability and statistics also, more so in probability. But if you're talking about a random variable, you could be looking at just simply the roll of a die. The set of outcomes are the sample space is 1 through 6, but a subset of that sample space would be maybe the even numbers, 2 and 4 and 6. In which case that would be a sub-sample space or a subspace. I mean, that's kind of a little bit of a reach because a part of the whole. Exactly. All right. So, in a real number system, you look at integers as being a subset of the real number system. So we're just applying this to vectors now. All right. The properties and conditions are the most important component. Obviously, well, it will be obvious.
So when we say like the subspace, that means you have a vector set of like a space of vector, right?
W is a subspace of real vector space V. Okay, so you have your vector space, which is going to be more encompassing, not necessarily all of real space, but it could be, or it could be itself a subset of real space. Zero vector of V is in W. That's the first property or condition that needs to be in place. Right? If you don't verify that, then you don't even bother with anything after that. Right? So the zero vector has to be in your subspace it has to be in your set in order to be a subspace. Right? So if the zero vector is not there, it's not a subspace. Don't even bother. If U and V are any vectors in W, then the sum of U and V would be in W. All right, so we would verify that. And if C is any real number, so a scalar, and U is any vector in W, then the scalar multiplication of C and U would also be in W. All right, so it's really just talking about span. It's talking about the idea that through a linear combination, you end up with other vectors that fall within the span of whatever the columns dictate. Right? So, but we verify these three properties in order to determine whether or not we're dealing with a subspace. All right. So I've worked out examples here just because they're of the simple variety. It didn't really warrant us actually physically writing anything. So W sub 1 is by definition the subset of R3. Right, that's the equal sign with three horizontals. Well, I'll just write it. It means equal by definition. All right, so basically we're defining W sub 1 as the subset, or as a subset, of R3 consisting of the vectors of the form A, 0, 0. Right. A itself belongs to a set of real numbers, together with standard addition and scalar multiplication. And we want to know, is W1 a subspace of R3? All right, so basically what it's telling us is that we need to verify the three components. Is the zero vector in the set? Can we get a vector of the same form as the given form through addition and scalar multiplication? If the answer to all three of those questions is yes, then it's a subspace. If not, then the answer is no. Right? So, well, it is possible if we're defining A as a set of all real numbers, then A can certainly be 0, in which case the 0 vector would be in the set. Right, so check. If I take the sum of any two arbitrary values in that real number system, I will get a number that's also a real number. All right, you just think about any possible pairing of two real numbers, add them together, your result is going to be a real number. It may not be pretty, but it's still going to be a real number. All right, so that checks out. And if I multiply a particular value, any value that I want, in that set of all real numbers by a particular scalar, will I also get a real number? Yeah. All right, so check, check, check. Therefore, this is a subspace. All right. So yeah, pretty basic. As far as proofs go, and like on every test, I throw a proof your way. This is kind of along the lines of what you might expect to see in this unit. So it's not like the world's most complicated kind of thing. It's like, check these conditions, see if in this general case, if it plays out. All right. And also, if you really think about it, if you have something that's in this particular form, it's a single column, but imagine it's part of a matrix. If it's part of a matrix and you go into reduced row echelon form, that's going to simplify down. It's already a pivot value, but it would simplify down to a 1, right, which would make it the basis of a system. Right? So if that's the case, then it would really make sense that it would be part of the subspace, because if it's actually the basis of a vector space, it's actually really saying it's not even just a subspace, it's the foundation of a subspace, because it's the foundation of the vector space itself. It's kind of like trying to think of something like a really small particle, like, I don't know. This might be kind of backwards, but you imagine like a tiny atom in a galaxy. And you say, well, is that atom part of the universe? Well, it's part of the galaxy, so of course it's part of the universe, because the galaxy's in the universe. But I want an analogy that goes the other way. It doesn't guarantee that just because it's part of the universe that it would be part of the galaxy. So, I got you one way. Converse isn't necessarily true. There was one example here that there was a typo, so I don't think it's this one. Let the real vector space V be the set consisting of all n by n matrices together with standard addition, scalar multiplication. Let W2 by definition be equal to the subset of B consisting of n by n diagonal matrices, is W2 a subspace of B? All right, so you have your all possible n by n matrices. Where do they put it? Oh yeah, there's the diagonal. Oh, that's my vector space. W2 is a subset with all diagonal matrices. And you can see it's diagonal. Everything off the diagonal is 0. All right. So if I take any two diagonal matrices and add them together, for example, I'll still get a diagonal matrix. All possible values, I mean, since we're dealing with real number systems still, the values along the diagonal could themselves be equal to 0, so that would allow it to be the 0 matrix, so that's checked out. And if I multiply a diagonal matrix by a scalar, it's going to be still a diagonal matrix. So we have it covered here, so therefore it is a subspace. So basically here we're just kind of defining it a little bit more verbally rather than in terms of just the general form, like a squared, b, whatever as your a column vector. It's more like, here's the type, here's the form of the matrix that we're looking at. Will these operations preserve that form? If the answer is yes, then it's a subspace. If the answer is no, it's not. Okay, so here's a little bit of a difference. So we have a form of a squared b. Oh, actually, that's the one I just said. Together with standard addition and scalar multiplication, we want to know, is W3 a subspace of R3? All right, so it's a subset of R3, but is it a subspace of R3? All right, so A and B they belong to the set of real numbers. So if A equals B equals 0, then we'd have 0, 0 squared, 0, which would be the 0 vector. So that checks out. I'll do the scalar next. If I take some value, I'll say, does C multiplied by, all right, W3 still belong to the set of reals, in which case I'd get CA squared CB. You know, you can put in particular values if you want, just to kind of test it out. But if I choose like C equals 2, A equals 7, B equals -5, it really doesn't matter. It's still going to have that same form, real, real, real. Oh, let me see. All right. But then we need addition. All right. So we would want to know whether if we were to, through scalar, or not scalar, vector addition, come up with something that's still within the same set. All right. So that's a different story. So I want to distinguish between my two sets by using subscripts. So I'll use just subscripts of 1 and 2. The other ones we were just working with single vectors, so it didn't make a difference. You can put subscripts in if you want, but it doesn't matter. All right, so we'd have A1 plus A2, A1 squared plus A2 squared, and then B1 plus B2. Okay, so what we want to do is make a determination of whether or not this is a valid form of vector addition. All right, so really what it's saying is does this take on the same form as that? It's pretty easy to check because it's basically saying, can I represent this single thing in that form? Is that a quantity squared? Well, if I were to actually do the substitution, if I were to say, replace A with A1 plus A2, and then the A itself here with A1 plus A2. All right, what I would be doing is, I'm establishing, based on this vector here, I'm establishing that the value of A is A1 plus A2. Because it is a particular model. I mean, you kind of lose sight of that throughout the process. I'm going to use a highlighter here to make it look a little nicer. You lose sight of that throughout the process, but there is an algebraic relationship between the first term and the second term. Right? If I multiply by a scalar, I still have that same relationship. It's a scalar multiple. Right? I still have that a squared relationship between my two terms. But here, if I'm letting A be equal to A1 plus A2, which happened here, that's great. Then naturally, if A is equal to A1 plus A2, then A squared has to be A1 plus A2 as a quantity squared. But through vector addition, I got something else. Now, you kind of run into that issue because the number one error that's made on any math test in any class is forgetting to distribute a negative sign. The number two error is this. So you may think that these are equivalent, but they're not. All right, and that's because, in order to actually get this, you'd have to distribute it out. You'd have an inner term. You'd have a 2A1, A2, which would make this not equivalent to that. So therefore, W3 is not a subspace of R3. All right, but we have our theorem here, which tells us, and I told you this before, kind of stole my own thunder. We're talking about a subspace, really just talking about span, right? If you're spanning any particular space, maybe you're spanning all of vector space, but maybe you're only spanning part of it. If you're spanning part of it, then you're spanning a subspace, right? The good news is, because span is really referencing a linear combination, and we beat this to death in the first unit, all the conditions that required something to actually span out a plane or a line or whatever, those are still in play. So if you know something spans out a particular space, then you already know that it's a linear combination. If it's a linear combination, then it's a vector space. If it's a vector space, then it's already more than a subspace, or potentially more than a subspace. So if you already know that you have a linear combination or your vectors span out any form of space, then you have a subspace. There's really nothing to show here. This is one of the examples, I think, that had a typo. And mainly because it's like missing the part of the question that makes it a question. Yeah, I think this is the one, so let's get rid of that. All right, and so with this kind of background context in mind, it kind of makes this question very easy because we actually did something very similar to this. It says, for what values of H will Y be in the subspace of R3 spanned by V1 and V2? All right, so if you're talking about spanning a plane. Like I said, it could be anything. It could be a plane. It could be a line. It could be any type of region. The idea here is this going to be within the span created by V1 and V2? So it's basically saying if we have weights on V1 and V2, C1 V1 plus C2 V2, will that be equal to Y? So what does that tell us to do? Like, one of the three things that we do in this course so it's some kind of operation, whether it's addition, matrix multiplication, reduced row echelon form, or determinant. So far, that's really the whole course is boiled down to those three things. Just a question of knowing when to do what. Right. So in this case, if we want to show that it's spanned by those two vectors, and we want to show that it can be written as a linear combination of the other two vectors, which means reduced row echelon form, find the two weights. Oh, what am I doing? It's got an H in it. Actually got to do some work. All right, so I need the 2 on the bottom to go away, so 2 R1 plus R3. So 0, 3, 2H minus 5. I'd like the 2 on top to go away, although as it'll turn out, it's not really necessary, but I'm kind of particular about these things. So 2 R2 plus R1. So 1, 0, H minus 6. As we know, in order to show a linear combination or a vector span a space, a subspace in this case, we just need to show that a solution exists. Right? So we have our two pivot values, so I want that 3 to go away. So I'm going to do a negative 3 R2 plus R3. Zero, 0, so now it's in an echelon form. 2H plus 4, thanks. All right, so in order for this to play out, I just don't want to have a pivot in the last column. So any non-zero entry in that last column will make a solution exist. So 2H plus 4, set it equal to 0, I get H equals negative 2. So if H equals negative 2, solution exists. Y belongs to the span of V1 and V2. And I'm not going to really address subspace, one, because they didn't really ask us to, but also because they said Y will be in the subspace of R3 spanned by V1 and V2. So they're already saying that V1 and V2 spans its own subspace, right? So, you're talking about two vectors in 3 dimensions. If you're talking about two vectors in 3 dimensions, you're talking about a plane. So it's basically defining the subspace of R3 as the plane that has these two component vectors. All right. So maybe we could do that.
So no free variables, right? So that means.
Say it again.
Therefore, there's no free variables. That's why it's like solution for this.
There is no free variables, yeah, because we were only looking for C1 and C2, and we have our weights. So let me just extend this a little bit. So the two relevant vectors, the two spanning vectors, these two guys. So 2i so 7 minus 4 is 3, so negative 3j, and then k would just be 1, yeah, so plus k. Right, so this would be the normal vector. In order to have a subspace, it has to have the 0 vector, so you can assume zero, zero, zero. Right? Because if it has a 0 vector, it must have the 0 coordinate, meaning it's going through the origin. So we're looking at a plane with a normal vector of 2, negative 3, 1. So the subspace of R3 that they were referencing up here, because it's spanned by these two vectors in 3 dimensions. Again, it belongs to the span of V1 and V2. But specifically, it's going to be equal by definition. Let's not get too fancy. I don't know if it's by definition. 2x minus 3y plus z equals 0. And since we can write the other vector, the last one here, the h negative 3, 5, in order for the solution to exist, we needed h to be equal to negative 2. Negative 2, negative 3, 5 should be in the plane. I just don't know how to write it. So we have vector negative 2, negative 3, negative 5. Corresponds to the point, the tip of that point would be negative 2, negative 3, negative 5. And so we can do a quick check. So negative 4 plus 9 minus 5, 0 equals 0. So checks. So a little extension stuff there, but something to do. Because by definition of a subspace, so the first condition is it has to contain the zero vector. And if it has a zero vector, it has to have the zero coordinate. It has to go through the origin.
Two things. Where did the -2 like that?
So once we solved for the h here, I just went back to vector y and just backfilled it in.